So welcome to this session. So in this session we are going to discuss about different phenomena of charge whenever it is placed in some material. Till now we discussed about the phenomena which are related to the charge in free space or vacuum. Now we are going to observe whenever we are placing a charge in a dielectric medium or whenever we are placing a charge in a conducting medium, what happens to that and what are different parameters we can observe for that. That the electromagnetic theory now will be observed. Once again it is electrostatics only. The electromagnetic theory will be observed in materials. So let us start with electrostatics in materials. So before that, just in brief we will examine what are different materials we have. So we have majorly two types of materials. They are conductors and insulators. Here in our electromagnetic theory we will call those insulators as dielectrics. So the materials will be classified as conductors and dielectrics. So when a particular material is called as a conductor, whenever it possesses some conducting nature means it can carry some current. So whenever there are free charge carriers, in most of the cases they are electrons. Whenever we have excess number of electrons, so more number of electrons, then they can carry some current, then they are said to be conductors. So they can conduct. And that's purely depend upon the conductivity. That's if the conductivity is very much greater than 1, then the materials are said to be the conductors. And when the conductivity is very much less than 1, this is sigma is very much less than 1, then they are said to be the dielectrics. Here exclusively we are calling them as dielectrics because they can possess two different types of electrical materials. Sometimes they will be acting as insulators and sometimes they will be acting as conductors. So purely depend upon the condition what we may choose, or so purely depend upon the applied electric field or some external conditions, that they will act as conductors as well as insulators. That's why we will call them as dielectric materials. This is the basic criteria for classifying the materials. Now what we do is we will examine when we place a charge in dielectric, what happens to it. When we place a charge in conductor, what happens to it. So we will start our discussion with dielectrics, that a charge was placed in a dielectric slab or a dielectric medium, then what are different phenomena we can observe when we place that one. So let us take, we are considering a dielectric slab. In the dielectric slab we are placing a charge. Then, so what happens to it if the charge is moving? Just for that, consider a dielectric slab. Here I am considering a dielectric slab. Let us take, this is the dielectric slab what I consider, that every dielectric material will be categorized with its or characterized with its permittivity or dielectric constant epsilon. Now a charge was placed inside the dielectric slab and let us assume that charge was moving from a location A to location B. That whenever the charge is placed, let us assume that the charge is moving from this location to the location B. Then clearly observe what are the phenomena or what are the parameters what I am considering here. Let us take the charge density inside this dielectric slab as rho v. Since we are considering a volume of the dielectric material, so let us consider the charge density inside that one is rho v, volume charge density. And let us take the cross sectional area of this one, that what I am showing here as S. The cross sectional area of this slab is S. So whenever wherever we are taking that cross sectional area, at location A or at location B or at the end, whatever it may be, simply I am taking that one as S. So for our convenience, what I do is I will take the differential cross sectional area as delta S. And let us take the distance between these 2 points A and B as some delta Y. That is the differential distance what I am considering from point A to point B. And let us observe, so let us assume the velocity of our charge which is traveling in the dielectric slab as u. So just these are the parameters what I am considering to obtain a few parameters which are required for us, and they are very much essential to observe our Maxwell's equations. So let us take once again, this is a dielectric slab which is characterized with its dielectric permittivity or dielectric constant, and let us assume we are considering 2 points and the charge is moving from this point to this point. These are the 2 points what I am considering, and the charge density inside this slab is rho v, and the velocity of that charge is u, and the cross sectional area of this slab is delta s. Now already we know, so the basic current will be defined as, that is, current is equals to the charge by time. The rate of change of charge always possesses some current. Here what I am doing is I am observing the current which can be observed whenever the charge is moving from point A to point B. So that's why I am taking this current as a differential current which is observed in this differential volume. So the differential current delta I now can be written as the differential charge in that particular region divided by the differential time. But here clearly observe, the charge what I am considering is not an absolute charge, it is charge density. Since we are considering a volume charge, so clearly we have to say that it is a charge density. So we have to write down this charge in terms of its charge density. So clearly write down this charge in terms of its charge density, which is equals to, this can be written as rho v into, so that is a volume charge density multiplied with its volume, differential volume, that's what I am considering as delta v. That differential volume is nothing but the volume which can be occupied with this simple length multiplied with the differential surface. So this delta v can be replaced with that equivalent. So what I am doing is I will replace this delta v with its equivalent, that is delta s multiplied with delta y. That is the differential volume what I will consider for this particular small part, right? So divided by delta t, that what I am writing here. Already we know, so distance by time is always velocity. That what we assumed earlier as u, that is the velocity of our charge is nothing but u. So which is equals to rho v delta s into the velocity of our charge, which is nothing but the delta I, right? Now just bring this delta s to the left hand side. Since delta is not equals to 0 for an arbitrary surface we are considering, can bring it that one to the left hand side. So bring it left hand side. So delta I by delta s, which is equals to rho v into u. Now what is this term delta I by delta s? I by s, the current by area, current per area is nothing but current density. So here clearly this delta I by delta s can be replaced with a term or denoted with some parameter called as current density, and J, so we are denoting that one. So J is equals to rho v into u. This simple term is called as convection current. Since we are considering a dielectric slab, so this particular current is called as convection current. And what are the units of our current density? Current density units are current per area, that is ampere per meter square. If we want, we can check the right hand side term also. This is the velocity and this is our volume charge density. So if you consider these two, and let us check whether it is satisfying our units or not. For velocity, what are the units? Meter per second. So they are the units, that is meter per time. And volume charge density, coulomb per meter cube. So coulomb per time, coulomb per second is current. Meter by meter cube will be cancelled. So obviously what we get is ampere per meter square. So just you observe what are the units of the right hand side and what are the units of left hand side. Clearly we can say that this J is called as current density, and clearly in detail it is convection current density that can be described for any dielectric material. Now we will examine whenever a charge is placed in a conducting medium, what happens to that. That is the next case. Now we will examine what happens whenever a charge is placed in conductor and what is the current density equation for that. That exclusively that current density is called as conduction current density. Since the current density what we are observing is in conductor, that current density is called as conduction current density. Now we will define what it is and we will derive what is the simplified equation for that. So once again just recollect what is the equation for our convection current density. J is equals to rho v into u. So where rho v is the volume charge density which can be observed in the dielectric, and u is the velocity of our charge which is moving in the dielectric. Now what we have to do is we have to just replace this rho v which is meant for our conductor, and we have to replace this u with the drift velocity which is meant for our conductor. That we are assuming that the charges are moving in a conductor. So obviously the more number of charges will be there, and they will take a drift velocity in the conductor. That drift velocity will be replaced with this u. So this u will be replaced with that velocity, and rho v will be replaced with the charge density which is observed in the conductor. For that, what I do is just I will take this rho v initially. Let us assume a conductor will have n number of electrons. That I am assuming small n is the number of count. That's a count for electrons in our conductor. Since the most charge carriers in our conductor are electrons, I am taking the charge as electrons. That n multiplied with minus e. That minus e is the charge of each electron in a conductor. Is nothing but the volume charge density in any conductor. So clearly rho v can be replaced with this minus ne. That's a very simple one. Just the number of electrons multiplied with its charge. The charge is taken as negative charge because of it is an electron. And we have to replace our velocity. So to calculate that velocity, let us assume what is the force which is exerted by the charge in conductor. Already we know the force can be written as mass into acceleration, where m is the mass of our electron. So mass into acceleration is the force, which can be written as mass into acceleration can be written as velocity by time. So force is equals to mass into acceleration, m is equal to m into u by t. That what we can write. But the same force can be calculated in terms of the charge and electric field intensity also. That I have to take the how much electric field intensity is existing there and how much charge is there for that particular electron. If I multiply them, obviously what I will get is the force. This is that what we learned from our Coulomb's law. So the same force can be obtained from force is equals to the charge is minus E. That is the charge of our electron multiplied with the electric field intensity what we have at that particular conductor. So just this is a force what we are calculating from the mass and acceleration. This is a force what we are calculating from its charge and electric field intensity. Both are same. Just make them equal. That is mu by t is equals to minus E. From this one, obtain this velocity, that u is equals to minus t by m. Now what we got is the force, from that force we got the velocity, and already we got volume charge density. Just multiply them to get this current density J. So to get the current density J is equals to, I am taking this minus Ne, that is nothing but the total volume charge density in the conductor multiplied with this particular term EET by m. So just what I do is I will rearrange this equation in such a way that to get a beautiful form, that is n e square t by m. This is a term what I take multiplied with E. So simply J is equals to some term. I will take sometime, for some time I will take this one as a constant k. So n e square t by m into E. Now I want to analyze what is this constant. After analysis, definitely I will get a very good equation for this one. So first, for the analysis of this k, what I do is k is equals to, I will write down like this, J by E. So k is equals to J by E. Now write down the units of this J. So the units of J are ampere per meter square. And what are the units of E? Volt per meter. So if you just rearrange this one, what we get is ampere per volt divided by meter. That what we get. So ampere per volt divided by meter. Volt per ampere is the resistance, right? But ampere per volt is nothing but the reverse of that one called as conductance. So here clearly this is the conductivity term that what we have, and we have to replace that one with mho or Siemann. The symbol is mho, or so you can write that one as Siemann. So it is mho per meter. The constant what we assumed here, that is Ne square t by m, is nothing but mho per meter, called as conductivity of the material, and denoted with a symbol sigma. That what we discussed in the beginning of this class, that is nothing but the conductivity of the material. So the conductivity of the material is equals to Ne square t by m. Now you can write this equation J as, now we can write this J equation as J is equals to just sigma E. So this is the equation for conduction current density, and the units are same. This is also ampere per meter square. Let's say earlier J is equals to rho v into U. That is the equation for convection current density. From that equation we derived a new equation, that is J is equals to sigma E ampere per meter square. This is called as conduction current density, and exclusively here the sigma is called as conductivity of the medium. The electric field intensity is E itself. Now we need to interpret this equation. What is this equation? So this equation resembles another equation which is earlier known to us. Now examine. Just what I do is I will try to write down the units of all these things. If you take the units of all these things, then obviously we will get a very good equation. So the left hand side units are ampere per meter square, which is equals to, on the right hand side what we have is mho per meter. The units for sigma are mho per meter. That what I write, mho per meter multiplied with this E. E units are volt per meter. Right, meter square, meter into meter will be cancelled. So what we get is ampere is equals to mho multiplied with volt. So mho multiplied with volt can be written as simply volt divided by ohm. That's the conductivity is inverse of our resistivity. So volt divided by ohm, that what I do is I will write down the equivalents of all these things as I is equals to volt, V divided by ohm is R. This is a very good equation which is known to us. V is equals to IR. This is Ohm's law. Right. Now clearly, if we are taking this J is equals to sigma E, and after analysis what we are getting is Ohm's law. So what I can say is that this J is equals to sigma is also called as Ohm's law in point form, which is applicable for electric fields. So clearly and exclusively this Ohm's law is suitable for conductors, so which what we are considering in our electrostatics. So whenever a charge is placed in our conductor, this Ohm's law is suitable, it satisfies. That's why this J is equals to sigma is called as Ohm's law for electric fields. The next concept what we are going to discuss is the continuity equation. This is one of the important equation which describes a very important feature in our upcoming Maxwell's equations. This continuity equation can be derived in a very easy way, that what we have to do is just we have to observe how much current is leaving through a closed surface. That whenever we are observing the current leaving through a closed surface, then that leaving current can be equated to some other thing which is inside that particular closed surface. That is nothing but the volume. So here clearly the continuity equation or the continuity theorem what we can say in our electrostatics will be like this. The total current leaving from the surface is equals to the rate of decrease of charge. So within that particular medium what we have. That's within that particular closed surface what we have. So here what we are doing is clearly we are observing how much current is leaving through this closed surface. So let us take this is the current which is leaving through the closed surface. Then the leaving current is equals to rate of decrease of charge. Since it is leaving, the charge can be decreased. So clearly this continuity equation is satisfies if and only if there is charge conservation. If the charge is accumulation, then definitely remember that this continuity equation will not applicable. The charge should be conserved, that if there is any charge conservation, this continuity equation is satisfies. So the current leaving, that I will write that one as an expression. The current leaving is equals to rate of decrease of charge. That the decrease of charge, rate of charge is dq by dt, and this negative sign is very important. That represents the reduction in the quantity. So the current leaving from the surface is equals to minus dq by dt. That what we have. And here clearly observe this I is not absolute current, that what we have here. This Q is also not absolute charge, that what we have here. Since we are considering a closed surface, from the surface we can obtain the current using its current density J. Right. In the same way, the absolute charge can be observed from its volume charge density rho V. So what we have to do is just we have to replace this current in terms of with our J, and we have to replace this Q with the equation what we have in terms of our rho V. So what I do is I will write down this current leaving from the closed surface. That is, this is our surface integral, and which is closed. A surface integral of current density J ds. This is the equivalent of our current what we have leaving from the surface, which is equals to minus d by dt of this absolute charge can be obtained from its volume charge density, and that is the volume integration of rho v dv. That what we have. Just this is the replacement of current, and this is the replacement of our, that's a minus dq by dt. Next, just what I do is I'll rearrange this equation by applying a beautiful theorem called as divergence theorem. Here what I have to do is I can apply divergence theorem to simplify this equation. Since it is a closed surface integral, we can apply divergence theorem. So apply divergence theorem here, then this will be converted to the volume integral. A surface integral can be converted as volume integral, and this can be written as del dot j dv, which is equals to, and clearly observe this volume integral is in terms of our spatial quantities x, y, z. And this is dou by dou t term. D by dt term is with respect to time. So we can swap these two operations. That is a volume integral of minus dou rho v by dou t dv. That's what I can write. And clearly, if you bring this one to the left hand side, then this becomes del dot j plus dou rho v by dou t dv is equals to 0. So clearly observe this equation where what we are considering is an arbitrary volume. For any arbitrary volume, if this integration is 0, then definitely what we can say is this integrand must be equals to 0. That is del dot j plus dou rho v by dou t is equals to 0. Del dot j plus dou rho v by dou t is equals to 0 corresponds to del dot j is equals to minus dou rho v by dou t. This equation is called as continuity equation, and which can be applied for many parameters, many observations. That divergence of current density is equals to rate of change of volume charge density, and it is decreasing. So clearly the divergence of current density is equals to the rate of change of current density, and it is a decreasing quantity. And clearly if there is no charge, then del dot j is equals to simply 0. There is no charge, del dot j is equals to 0. And for steady current, if steady current also we are considering, this del dot j is equals to 0. So for clearly, so del dot j is equals to 0 corresponds to the current density is not diverging. Current density is not diverging means the incoming current is equals to the outgoing current. That's what we can say. So whenever we have some volume, how much current which is coming to the volume, which must be equals to the current which is going out from the volume. Just if you recollect the concept what we learnt in our circuit theory, which is same as our KCL. That in KCL also what we have is a node. So whenever we are observing the total input current to that particular node, then that must be equals to the total leaving current. Here the total input current is equals to the total leaving current. If it is a steady current, that what we can say, then del dot j is equals to 0. This is a simplified continuity equation. This continuity equation is very much useful in observation of our Maxwell's equations later. So clearly remember that this del dot j is equals to minus dou rho v by dou t is very much useful. Here we are going to observe a very interesting phenomena, that whenever a charge is placed in dielectric medium, how much time it will remain as charge, or whenever a charge is placed in conducting medium, how much time it will remain as charge. That what we are going to observe. Because to store some electric energy, so what we require is charge. So whenever we are placing that particular charge in volume, that must remain as charge for long duration. So we will examine how much time a particular charge will remain as charge for long duration with the help of our relaxation time. So later I will define what is this relaxation time also. For that what I do is I will take what are all the equations what we have till now, and I will try to rearrange them. So let us take the continuity equation, that is del dot j is equals to minus dou rho v by dou t. So just now we derived this equation, del dot j is equals to minus dou rho v by dou t. And from the Ohm's law, that what we learned earlier, that is in point form, that is j is equals to sigma e, that what we have, just substitute here, then del dot sigma e is equals to minus dou rho v by dou t. And clearly this can be written as sigma del dot E is equals to minus dou rho v by dou t. And once again recollect the equation what we derived from our Gauss law, that is del dot D is equals to rho v. Since we are considering some material which contains some charge, so del dot D is equals to rho v, that what we have to consider. And this can be written as del dot epsilon E is equals to rho v, where epsilon is the permittivity of the medium. This can be written as epsilon del dot E is equals to rho v, which corresponds to del dot E can be written as rho v by epsilon. So what I can write is this del dot E can be replaced with rho v by epsilon. So here I will replace that one. Sigma rho v by epsilon is equals to minus dou rho v by dou t, that what we have. Just rearrange this equation. Rearranging this equation will give us dou rho v by dou t plus sigma by epsilon rho v is equals to 0. So clearly observe this equation. This equation is a linear equation and it is a single order differential equation. So directly we can obtain the solution for this one by substituting its boundary values. That is, at time t is equals to 0, what happens to that one, like that. So after simplifying this one, we can obtain the solution for rho v as rho v naught e power minus t sigma by epsilon. This is the solution for this particular equation. Now we need to analyze this equation. So what is this equation, and what is this rho v naught term, and what is this sigma by epsilon or epsilon by sigma term? That if we analyze, then obviously the solution for our previous question, that how much time a charge can be remains for us as a charge, is easily obtained. So analyze this particular equation. So consider this equation, that rho v is equals to rho v naught e power minus t sigma by epsilon. That just I'll rearrange this one and I'll write this one as rho v naught e power minus t by tr. Simply by observation we can say that this tr is some other term which can be written as tr is equals to epsilon by sigma. For some time just don't take any name for this one, name it as tr itself. Okay, tr is equals to just epsilon by sigma. Now what is this rho v naught? Rho v naught is the initial charge density. Whenever this time t is equals to 0, rho v is equals to rho v naught. So initially it's without doing anything we are observing the charge. That charge is nothing but your rho v naught. So clearly this is our charge density at time t is equals to 0. That what we can write. Now how the relaxation time was defined? The relaxation time was defined like this. So it is the time taken by the charge to reduce its quantity to 36.8% of its initial value, or the time taken by the charge to reduce the initial quantity to e power minus 1 times of the initial value. So here what we are doing is just we are observing the time. Whenever we are placing a charge, we are observing the time after which time this charge was reduced to 36.8% of the initial value, or e power minus 1 times of the initial value. That what we have to examine, right? So here clearly what it is, I'll examine this equation, that this rho v will be reduced to how much extent? 36.8% of the initial value. So that rho v is equals to, clearly we can write rho v naught into 36.8%, or the same can be written as rho v naught into e power minus 1 times. So here clearly at this particular time, clearly write down here, at relaxation time, the rho v at relaxation time was reduced to 36 times of the initial value. Now make them equal to get a beautiful equation, that rho v naught e power minus 1 is equals to, which is rho v naught e power minus t by tr. That what we wrote. So by the comparison clearly you can say that t is equals to tr. That this tr is nothing but the time where we got the initial charge density was reduced to 36.8% of the original value. The charge density will be reduced to 36.8% of the original value. So here clearly the expression for this tr, now definitely we will call this tr as the relaxation time. So tr is equals to epsilon by sigma. So the notation what we took as tr is so appropriate one and most suitable. So tr is equals to epsilon by sigma is called as the relaxation time, and after that time the total charge will be less than 36.8%. So up to that particular time the total charge will be greater than 36.8. After that time the total charge will be less than that 36.8% of the initial value. So if it is less than 36.8, that may not be useful for any application. So we can't use that one for generation of the electric field intensity, or the electric field intensity what we are getting or the potential what we are getting may not be useful for us. So to store some electric energy, what we require is this relaxation time must be more. So if this relaxation time is less, then immediately the charge will takes its recombination and that will disappear. So since there is no charge, no potential, no electric field intensity. But if this relaxation time is more, that the charge will takes more time to get relaxed, That's why we can get as electric potential or field for longer duration. That simply based on this one, that's how we can examine. So for a dielectric medium, what about the relaxation time? And for a conducting medium, what is the relaxation time? With the same simple examples, we will examine that. So the relaxation time, what we derived is TR. The notation is TR is equals to epsilon by sigma. If you observe clearly, it's purely depend upon the material characteristics only, that is epsilon and sigma only. For a dielectric, let us consider, we are considering a dielectric, and in the dielectric slab we are placing a charge. Let us consider epsilon r is equals to 5 for that particular dielectric. Since it is dielectric, the conductivity is very, very small. I will consider that one as 5 into 10 power minus 12 mho per meter. That is the conductivity of the dielectric material. That's what I am considering. Now substitute here TR is equals to epsilon. Epsilon is equals to epsilon naught epsilon r divided by sigma, which is nothing but 8.854 into 10 power minus 12, and epsilon r is 5 divided by sigma is 5 into 10 power minus 12. So 10 power minus 12, 10 power minus 12 will be cancelled, 5 will be cancelled. So approximately it is equals to 9 seconds. So whenever we are considering a charge, and if you place that charge in dielectric medium, what we get is approximately for 9 seconds that charge will remain as charge. Now the same phenomena we will observe for conductor also. Let us consider a conductor. For conductor, let us take epsilon r is equals to 1 and sigma is very, very high. That is, let us take some 5 into 10 power 8 mho per meter. That's approximately we are considering copper here. So epsilon r is equals to 1, sigma is equals to 5 into 10 power 8 mho per meter. Then the relaxation time, the same relaxation time I am calculating here. So which is equals to epsilon naught epsilon r divided by sigma. Epsilon naught epsilon r is 8.854 into 10 power minus 12 into 1 divided by sigma is 5 into 10 power 8. So after calculation of this one, so approximately what we get is here 1.5. So this is approximately 9, 1.5 into 10 power minus 22nd. So just you observe the time, how much time the charge will remain as charge, it is less than picosecond. So very, very small quantity. So whenever the charge is placed inside the conducting medium, immediately that disappears. That will not appear in the volume. So what happens to that? Whenever you are placing a charge inside the conductor, immediately that accumulates at the surface of the conductor and appears as surface charge. So here clearly observe, with these two examples we can say, so whenever we are placing our charge in dielectric, that charge will remain as charge for approximately 9 seconds. After that only the charge may disappears or it reduces. But whenever we are placing our charge in conductor, immediately or almost all immediately that will disappear and accumulates at the surface. So to store our electric energy, what we require is a dielectric material. So clearly to store our energy, electric energy as a conducting material is not suitable. That may be suitable for generation of the charge or having the charge on its surface, but so to store that particular charge inside the volume, we are not supposed to take any conductor, we are supposed to take a dielectric material. So here based on the simple principle, a very good device is called as capacitor was made. It's already we know a capacitor is called as a electrostatic device and electric device which can store electric energy. How that electric energy can be stored, that we will discuss now. Now we will discuss about these capacitors. So what is a capacitor and what is the basic structure of capacitor? Let us take, we have two conducting materials. This is one conducting material and this is another conducting material. So between these two some potential difference was applied. Let us take, this is a potential difference between these two. Let us consider this is A and this is B. A potential difference of VAB can be observed between these two. That what we are doing is we are applying the potential, right? So clearly this will comes a negative charge and this becomes a positive charge. On the surface of that conductor, definitely some charges will be accumulated. Since there is some charge, electric field will be observed and that electric field will flows from always this positive charge to negative charge. Like this. Let's say already we know this is a source and this is our sink. And if I place any dielectric medium between these two, that this particular region was filled with a dielectric medium of epsilon, permittivity epsilon, then obviously this particular structure or arrangement can store some electric energy. That what we have is a charge, and that charge is generating the electric field. That electric field can be stored inside the dielectric slab what we are placing between these two materials or these two conductors. Simple. This arrangement is called as the capacitor arrangement, and it has a capacity. Why it is called as a capacitor? It has a capacity to store the electric energy. How that capacity is defined? That capacity is called as capacitance. How that capacitance is defined? That capacitance is defined as and denoted with symbol C, and it is defined as the total charge what we can store per applied potential. This is the potential what we have. So the total charge what we can store here per applied potential, that what I write is VAB. So this simply, this is a very simple equation for our capacitance, and if you observe what are the units for this capacitance, coulomb per volt. But this is not widely used unit, that instead of this one what we use is farad. On the name of scientist Farad, simply what we use is capacitance units as farad. Now we are trying to obtain a simplified equation for this one in terms of this charge and potential. So to obtain how much charge we have here, what we have to do is just we have to observe the flux leaving through this one. So if you observe the flux leaving through this closed surface, then which must be equals to the total charge which is enclosed by that particular surface. So what I do is I will replace this charge with flux, electric flux, that what I am considering here, and this flux can be calculated using its flux density. So what I do is I will replace that flux with the surface integral of ds. That here we are considering a closed volume or a closed bounded or material, a conducting material. Since it is a bounded conducting material, a closed surface integral of ds will gives us the flux. That flux must be equals to the charge. And already we learned the equation of potential from the electric field intensity which can be observed between these two is minus line integral of E dl. That here I am taking the magnitude. Since we require the absolute value of the capacitance, here I am considering the magnitude only, and replace this d with epsilon E. Let us take the homogeneous medium what we are considering. So d is equals to epsilon E dot ds, that what I can write, divided by line integral of E dl. So clearly observe this line integral is open line integral, that is always from positive charge to the negative charge, right? And it should not be closed integral. If it is closed integral, obviously this term must be equals to 0. So don't take this one as closed, but this is the closed integral as per our original observation. So which is equals to, simply this equation can be written as C is equals to epsilon surface integral of E ds divided by line integral of E dl. Simply this is the equation what we are supposed to use to obtain the equation of our capacitance for any type of capacitor. That here as an example we took two conductors, that these two conductors may be of any shape, that the conductors may be of flat sheets, or the conductors may be of some coaxial cylinders, or the conductors may be of some spherical cylinders. So purely depend upon the type of sheet what we are considering or the type of conductor what we are considering, this capacitance equation may varies, but this is the basic equation that what we have. C is equals to epsilon surface integral of E ds divided by line integral of E dl. So using this one we will try to derive equation of capacitance for one type of capacitor, and later we will observe what is the capacitance for remaining. Now we will examine what is parallel plate capacitor and what is the capacitance of that parallel plate capacitor in easiest way. That the name itself indicating parallel plate, that we have two parallel plates. The two conductors are simply two parallel plates, and for our mathematical convenience I will take those two parallel plates along x-axis. Let us take this is one parallel plate and this is another parallel plate. That two parallel plates are placed here, and for our convenience once again try to draw them as plates. It's better to understand. So these two are the two plates what we have. Let us take the distance between these two plates is d, and the space between these two plates was filled with some dielectric material with permittivity epsilon, dielectric constant epsilon. And let us consider the cross sectional area of these plates is S. So here simply what we are doing is we are trying to observe what is the capacitance of a parallel plate capacitor. Before that, just this is the structure what we have. Two parallel plates will be there. Those two parallel plates will be kept apart of a distance d, and between these two parallel plates we have some dielectric material. And finally, let us take this plate was positively charged with the applied potential, and this plate was negatively charged with the applied potential. Now what we have to do is we have to obtain the electric field intensity between these two, and using that electric field intensity and substitution in our base formula, we need to obtain the capacitance. So what will be the electric field intensity because of the top sheet, and what will be the electric field intensity because of the bottom sheet? That's what we want. Already we learnt the electric field intensity because of the sheet as rho s by 2 epsilon. In our free space it is epsilon naught. Since we are considering some medium, let us take this one as epsilon. So rho s by 2 epsilon in the direction of normal to that particular sheet. So here what we have to do is we have to take the electric field intensity because of the positive sheet. That what I am writing as E plus. That the electric field intensity because of the positive sheet, that is nothing but the top sheet, which is equals to, since it is positive charge plus rho s, that what I am writing, by 2 epsilon. And what will be the electric field intensity direction? Normal to this one. At which location you are calculating the electric field intensity? Between these two plates. So this is the region normal to this plate, and in this region clearly it is negative x direction. So clearly observe, this is the positive x direction, and the direction of the electric field intensity because of this sheet is negative x direction. That's why what I am writing is here minus ax. So simply this is the electric field intensity because of the positive sheet. In the same way, obtain the electric field intensity because of the negative sheet. So the electric field intensity because of the negative sheet in the required region will be in this direction. That is positive x direction, but it is negative charge. That's why we can write this E as E minus, that is the electric field intensity because of the negative charge, which is equals to minus rho s by 2 epsilon ax. Now the electric field intensity because of the positive charge is rho s by 2 epsilon, that is in the direction of negative x, and the electric field intensity because of the negative charge, which is equals to minus rho s by 2 epsilon in the direction of positive x. So what will be the total electric field intensity in this region? The total electric field intensity is the summation of these two. That is, E can be written as E plus plus E minus. So if we add these two, what we get is simply minus rho s by epsilon ax. So simply this is the electric field intensity what we have. Now to get capacitance and to substitute this particular equation in our formula, we require differential length as well as differential surface. So the differential length, that is nothing but the distance between these two, is also in the direction of x. So this is the direction of dl, that what we can take. And the differential surface, this is the surface what we have, this is the surface what we have. And if you observe, with the observation we can say that the differential surface is also in the direction of x. So clearly dl is in the direction of x, ds is also in the direction of x. I don't want to write down any equation, just I'll mention here that dl is in the direction of x, that is dl ax, and ds is also in the equation of x, that is ds ax. So in the equation what we have is a dot product between this electric field intensity in dl, electric field intensity and ds. So ax dot ax will exist for us. So what we do is try to we will substitute all these parameters in our basic equation of capacitance. What is the basic equation of capacitance? Already we gone through that one. Epsilon closed surface integral of E ds divided by a line integral of E dl. So directly, don't go for any calculations or any other. Directly observe E dot ds will exist for us. Both are in x direction. E dot dl both are existing, and which both are in x direction. So directly what I am doing is I am trying to write down the equations that epsilon, it is surface integral of, instead of that E ds, that what I write is minus rho s by epsilon ds, E ds, that E dot ds is E ds, right, divided by, this is a closed surface, right, line integral of E minus rho s by epsilon, this is our dl. So directly I am writing them, and clearly observe this rho s is uniformly distributed charge and it is a homogeneous medium. uniformly distributed charge, homogeneous medium. So we can bring it out from the integration. So just brought it out from the integration, then the equation now becomes epsilon minus rho s by epsilon surface integral of ds divided by minus rho s by epsilon line integral of dl. Once again, just observation is required here, don't go for any calculation. Rho s by epsilon, both are constant, so just cancel them, epsilon remains for us. Surface integral of ds, is nothing but the surface area of the sheet what we are considering. The surface area of the sheet can be replaced with s. In the same way, line integral of dl is nothing but the distance between these two plates, that this can be replaced with d. So this entire term can be replaced with s, this entire term can be replaced with d. Therefore, the equation of capacitance now can be written as C is equals to epsilon A. A is the area, so that the same can be written as S, epsilon A by D or epsilon S by. Simply, this is the equation of capacitance for a parallel plate capacitor. Now observe, what is the equation of this capacitance? Just epsilon S by D. Epsilon is the characteristic of the dielectric what we have here. S, surface area of the plate. D, distance between the plates. But what is the initial definition of our capacitance? Capacitance was initially defined as C is equals to the charge stored per given potential. Right, it is defined in terms of charge and potential, but after derivation there are no residues of charge or potential here. Just it's purely dependent upon the physical arrangement of the material or structure what we have. So clearly what we can say is this capacitance is the physical phenomena of the arrangement. It's nothing more than that. So if you change the distance between them, the capacitance will vary. If we change the cross-sectional area, the capacitance will vary. So simply we can remember that C is equals to epsilon S by D is the formula. It's a very useful formula which can be useful for calculation of the capacitance of a parallel plate capacitor. In the same way, we can get the equation of coaxial capacitor or a cylindrical capacitor and spherical capacitor also. But directly what I do is I will give you the equations just to try to remember them. They may be useful for solving few problems. Now the same capacitance can be observed for a coaxial capacitor. Let us take a coaxial capacitor or cylindrical capacitor. That two coaxial cylinders that will be placed like this. That is, the inner cylinder was positively charged and the outer cylinder was negatively charged. Once again, what we have to do is we have to obtain the electric field intensity between these two conductors and substitute that electric field intensity in the basic equation. Then what we will get is the capacitor. But what I do is directly I will try to give you the equation for that. The capacitance of a coaxial capacitor is 2 pi epsilon L divided by natural log of B by A. Just once again observe here, this B is the outer radius and A is the inner radius of the cylinders. This is also purely dependent upon only material and the structure characteristics. It's not depending on the potential what we are applying, and it's not depending on the electric field or charge. So clearly C is equals to 2 pi epsilon L, length of the cylinder, B outer radius and A inner radius. In the same way, if you observe a spherical capacitor means two spheres will be there. Let us take the inner sphere of radius A and another sphere with same center, that is these two are concentric spheres. Outer sphere has radius B. Then definitely we need to observe the potential, whenever the potential is applied we need to observe the electric field intensity between them, and using that electric field intensity we have to obtain the capacitance, and the final equation will be like this, that is 4 pi epsilon divided by 1 by A minus 1 by B. So if you observe this equation also gives a simple relation between the capacitance and the physical phenomena, physical characteristics of our physical parameters of our capacitor, right? So here clearly remember, whenever we have a capacitor, that capacitor must be made up of two conductors. That one conductor is positively charged, another conductor is negatively charged, and the electric field between those two must be calculated, and using that electric field intensity we can obtain the equation for our capacitance. So these are the equations for our, earlier we have equation for our parallel plate capacitor, now this is the equation for our cylindrical This is the equation for our spherical capacitors. Now the energy stored in any capacitor we require. So how much energy it can store? That already we know the energy stored in any volume for an electrostatic device is equals to WE is equals to the volume integral of d dot E dV. That's multiplied with the constant 1 by 2. So here clearly the total energy stored in any given volume whenever there is some electric field intensity is this one. So just what we do is we will try to simplify this equation by writing this d as epsilon E, volume integral of epsilon E dot E dV. That what we have here, right? E dot E is always E square. So this can be written as 1 by 2 volume integral of E square dV. So if we take this E and substitute here, definitely what we get is the electric field intensity equation will be substituted here, and that definitely what we get is the total energy stored in any type of capacitor. As an example here, what we do is we will try to take the parallel plate capacitor and we will substitute E here and try to obtain the equation for the energy stored in that. Now what is the equation of electric field intensity in parallel plate capacitor? E is equals to, here what I am taking is the magnitude. Here E is equals to, the electric field intensity is rho s by epsilon. That here what I am doing is just I am taking the magnitude. I don't want to consider any direction for this one. Just what I do is I will substitute here, right? Then the total energy which is stored is equals to 1 by 2 volume integral of E square. E square is nothing but rho s by epsilon whole square multiplied with dV. Here a small modification is there. Here we forgot to write down this epsilon here. So what I do is I will write down epsilon also here. That the epsilon will be added here also. That is 1 by 2 volume integral of epsilon rho s by epsilon whole square dV. So which is equals to 1 by 2 rho s square by, it's integration, it's a volume integral, rho s square by epsilon dV. That what we have. That rho s square by epsilon square epsilon will be cancelled, and this is our dV, right? So which is equals to rho s square by epsilon volume integral of dV. That what we have. Now what is this volume integral of dV? Volume integral of dV is nothing but the total volume occupied by the capacitor. Here what we are considering is a parallel plate capacitor. So what is the total volume occupied by the parallel plate capacitor? The surface area, cross sectional area is S and the distance between them is D. So S into D will give us the total area occupied by the capacitor. So instead of this volume integral of dV, I can write that S into D. So simply write down this one as rho s square by epsilon S into D is the total term, right? Now what is this rho s? Rho s is nothing but the surface charge density. The surface charge density is always defined as the total charge per given area. The given area what we considered for parallel plate is S, and let us take the total charge as Q. So this rho s can be replaced with Q by S. So what I do is I will try to write down this one as Q by S. So before that what we have is here 2. This is also 2 epsilon. So rho s can be replaced with Q by S. So this can be written as Q square by 2S square epsilon S D. Just once again observe what I am doing. I am taking the total energy stored in any electrostatic volume. It's a volume because of the electric field, which is equals to 1 by 2 epsilon E square dV, right? E, that what I am taking from the parallel plate capacitor, and I am substituting here that 1 by 2 volume integral of rho s square by epsilon dV. After simplification what we get is 1 by 2 Q square by S square epsilon S into D. So the total energy stored now can be written as 1 by 2, that just observe here, this is Q square divided by S will be cancelled and this D can be brought out, that S epsilon by D. What is this S epsilon by D? Just now we observed that one as the capacitance of a parallel plate capacitor. So this can be written as capacitance. So which is equals to 1 by Q square by C. 1 by 2 Q square by C. This is the energy stored in our parallel plate capacitor. That we can use this equation. Or what is this Q by C? Already we learnt C is equals to Q by V. From that one Q by C is equals to just V, right? So this Q by C can be replaced with V. So which is equals to 1 by 2 QV. That what we can write. So the total energy can be stored in a capacitor can be calculated in the 1 by 2 Q square by C or 1 by 2 QV. Or if we want, we can write down this equation once again. Q can be replaced with CV. If Q is replaced with CV square, the same equation can be written as 1 by 2 CV square. Right, whatever it may be the equation, just according to the requirement, we need to modify this equation. The same equation is applicable for all the capacitors. Whatever it may be the capacitor we have, the total energy which is stored in that particular capacitor is 1 by 2 CV square or 1 by 2 Q into V or 1 by 2 Q square by C. Using this simple equation, we can observe the total energy stored in a capacitor. Now, we will discuss a few more points which are very important for boundary conditions, or to observe some other phenomena in the dielectrics, that they are a dielectric constant, a dielectric strength, and more importantly polarization. So what is the meaning of that particular word polarization? How it can be happened when we have some electric field? Just imagine we have a dielectric material. The dielectric material consists of different atoms. That each atom is a neutral atom, since the total charge which is embedded in this one is 0. The positive charge is equals to the negative charge. It is said to be a neutral atom. Now what I am doing is I am trying to apply some electric field intensity to it. That whenever the electric field intensity is applied in a particular direction, let us take this is the direction of electric field intensity, that what I am applying to the material, then what happens to it? Immediately we can observe a phenomena that this positive charge will move in the direction of that electric field, and the negative charge what we have will move in the opposite direction to the electric field. So after some time, so if you are keep applying the electric field intensity, after some time what happens is this same will becomes like this, that this is the positive charge which is moving in the direction of electric field, and the negative charge is moving away from the electric field. And after applying a sufficient amount of electric field and keep applying the electric field, then these two charges will be detached from the atom, and these two will becomes two individual charges of the same magnitude, and they will be about of some distance. Let us that this is our negative charge and this is our positive charge, and clearly observe these two charges will be in the direction of electric field intensity only. That the positive will be in the direction of electric field, and the negative charge will move away from the electric field intensity direction, right? But so clearly you can observe, so these two charges are of same magnitude. This particular phenomenon is called as the polarization. What we are doing is we are taking a neutral atom. That neutral atom will becomes two poles. This is a positive pole what we have, and this is a negative pole what we have. That what we are making it as a poles. That's why it is called as a polarization. So this particular phenomena, that how that polarization can be observed by applying our electric field intensity. It's not a simple electric field intensity. A sufficient quantity of electric field intensity must be applied. That quantity of electric field intensity is called as it's a dielectric strength. That the maximum electric field intensity what we are applying, till then the dielectric will remains as dielectric. After that electric field intensity, now the dielectric will becomes two poles. That particular electric field intensity, clearly remember this word, that particular electric field intensity is called as dielectric strength. So it is the threshold. Before that dielectric strength, dielectric will remains as dielectric. After the dielectric strength, the dielectric now becomes two poles. Two poles means two charges. Since we have some charges, definitely it will act as conductor. So clearly if you draw a boundary like this, this is the dielectric strength. So before this dielectric strength, our dielectric is clearly dielectric, and it will act as insulator. So there will be no charges and it's not conducting. And after the dielectric strength, it will act as a conductor. That's why the word dielectric. It will possess two electrical properties. It's possessing an insulating property as well as conducting property. That's purely depend upon the applied electric field intensity. This polarization phenomenon is very important for observation of the dielectric constant. So what is the dielectric constant? How it can be observed? So now just observe that polarization. That polarization was defined for different dielectric mediums like this. Polarization is denoted with P, which is equals to epsilon naught chi naught E. So clearly remember this one. This one is chi naught and called as susceptibility of the medium. So what is the sustaining capability of the dielectric material that can be observed using this chi naught? So this is the definition of the polarization from the basic definition of the susceptibility and other parameters. Now if you are observing the electric field and the electric flux density, that what we have, the electric flux density for a polarized material, it's not for a normal material, for a polarized material is the combination of the electric flux density along with the polarization. So simply the electric flux density what we are observing for any polarized material is equals to the normal electric flux density and it is added with the polarization what we have, simply which is equals to epsilon naught E plus epsilon naught chi naught E. Just rearrange this equation, that is 1 plus chi naught epsilon naught E. Now this is the modified dielectric electric field, electric flux density. This is the modified electric flux density for the polarized material. So the modified electric flux density is equals to 1 plus chi naught into epsilon naught into E. And we have a basic form for our electric flux density. What is the basic form for electric flux density? D is equals to epsilon E for any material. Just compare these two equations. If we compare these two equations, then clearly we can say epsilon is equals to 1 plus chi naught epsilon naught, where epsilon naught is the permittivity of the free space, right? So this particular term what we have can be defined as epsilon r. That epsilon r is said to be the relative dielectric constant of the medium that what we have. So the relative dielectric constant now can be written as epsilon r is equals to epsilon by epsilon naught. So if you want to define the relative dielectric constant, simply it is a ratio of the permittivity of the medium to the permittivity of the free space, or dielectric constant of the medium to the dielectric constant of the free space. And what are the units of our epsilon r? Simply no units. It is a relative term that we are comparing one with another. And how we can write this epsilon r? Epsilon r is equals to 1 plus chi naught. So clearly dielectric constant is a relative dielectric constant is the comparison between the dielectric constant of the medium with the dielectric constant of the free space.